Hello, everybody. I'm Ian Barnett. I'm an assistant professor of biostatistics at the University of Pennsylvania. Today, I'm going to be talking about estimating routine and sleep from sparse smartphone sensor data. So my group at Penn, a big focus of ours is on deriving from passively collected sensor data these various digital phenotypes, biomarkers, features, whatever you want to call them. And today I'm going to be talking about sleep, which has been notoriously difficult to estimate. If you look currently at forest, or if you look at rapids, right now you'll see there is no estimation of sleep that you can get from smartphone data. And there's a good reason for that. It's very difficult to estimate sleep. Now, if you have wearable devices, if you have an actigraphy watch, and if you wear it all the time, you can do a really good job of estimating sleep. But what happens if you stop wearing it? And that's just with wearable devices. With smartphone data, you could have great data, but you still have to worry about this disconnect, which I say here at the bottom here, this challenge, where smartphone activity may not be a perfect mirror for the behavior of the person, right? If you seldom use your smartphone, or if you stop using it an hour before your bedtime, and I just assume that smartphone activity reflects your sleep, then I'm going to overestimate your sleep by an hour before bed, essentially, right? So how do you overcome this problem? And that's what I'm going to show you, that we actually have a solution that works pretty well for that today. So the approach here is, I'm mentioning two things, sleep and routine. The goal here all along was to get a quality estimate of sleep when you have a lot of missing data, or even if your data is not missing, but if it's just sparse, right? Maybe you're not a big smartphone user, but you still want to get reasonable estimates of sleep. Can we still do something? Or is it a hopeless cause? And I'll tell you right now, it's not. And we can actually do a pretty decent job. And, but in order to get there, I'm going to be talking about two projects today, one of which we've published, and this is kind of a stepping stone to get to sleep, which is focused on routine. Routine is something which people have successfully measured in the past. I have, actually, in part of my work with JP when I was a postdoc with him, and we did it with GPS. Other people have done it successfully. But today I'll be talking about routine using screen state and accelerometer data, and there's a reason for that, which I'll get to. So I'll introduce the study that this was being applied to. There was a study run by Ted Satterthwaite, also at Penn, with 41 adolescents, young adults, with affective instability. And they collected smartphone data via BWI for 3 months. So the first thing we're going to do is we're going to see, can we quantify strength of routine in this cohort? And also, as an aside, even though, again, I'm saying this is a stepping stone to estimating sleep, we'll see, are there any associations between this routine measure that we come up with and mood and depression? So that'll be interesting to see along the way. So I mentioned the data types I'll be working with today. Screen state and accelerometer. Now, if you're measuring routine, there's no reason you have to restrict yourself to these two. But with the goal of sleep in mind, we are going to try to estimate routine in your phone use and use that as input into a model for our sleep estimation later. And because of that, these two sensors are particularly useful with respect to estimating sleep. And also, this presents a very interesting and actually, statistically speaking, an easy to address missing data problem if you have both screen state and accelerometer data. Because screen state data, it's never missing. If there is no screen on activity, we know there was no screen on activity. All of these events are recorded. So you can think of this as a data stream, which is, we have observed data everywhere. Whereas accelerometer data can certainly be missing. And so if our approach is going to try to use both of these simultaneously, this suggests that we can maybe do some imputation to infer accelerometer values if we observe both of them. Because naturally, screen state, if there's not a lot of phone use, then the accelerometer is going to be relatively quiet as well. So we have this very nice setup, right, where we have two data streams, one of which is always observed and is highly correlated with the other. So it gives us an opportunity to have a pretty successful missing at random MAR model for imputation. So we have such a model. We do a two-state hidden semi-Markov model. And one aspect here is that we include hour-of-day random intercepts because whether or not you're active on your phone probably depends on time of day. I will say these are also N of 1 models. These are models using just one individual at a time. So you do need enough data to essentially, probably over a month of data before I would feel confident in some of these models. So, but essentially what we do, the idea is pretty straightforward, but we're using a hidden semi-Markov model because we have these two latent states, one of which is, are we in a dormant or non-dormant? This is referring to your phone state. Because if we're in a dormant state, then when we do imputation, we want to essentially say, what would it be like, what's the baseline accelerometer levels? I'm talking about magnitude of accelerometer here. We're not actually imputing the raw accelerometer values. That's a much harder task. We're imputing hourly level average magnitude of accelerometer, and which is much easier to do and much lower granularity. But even still, it's still a tough problem. And if we've inferred that the phone is in a dormant state and it's missing, then our imputation model should replace it with what essentially inactive phone, if your phone is just resting on a table or something, what does your accelerometer look like? Essentially, that's what we want to use for your imputation. Whereas if we infer that you're in a non-dormant state, then we want an imputation model which relies on what your kind of distribution of your magnitude of acceleration looks like when you're using your phone and when we have observed data, right? So essentially there's these two distributions that depend on whether or not you're in this dormant or non-dormant state. So this has been a pretty successful model. As you might imagine, the likelihood that you're in this dormant state is much higher in the morning hours than it is when you're asleep versus when you're awake in the evening. So this approach has been fairly straightforward. Now, in the broad scheme of things, we did this imputation approach first on our accelerometer data, and then we're taking the imputed data, and now we're going to derive our routine metrics. So we have, this is a paper that we recently published in JMIR Formative Research, where we do a proportional hazards HMM model. And in this, this particular paper is under review in biometrics, but the results I'll show were the JMIR paper in a couple of slides. So there's kind of two papers that we got out of this. But this approach is relatively straightforward, but we're modeling these hourly screen counts in, this is a different HMM essentially, but in this case what we're doing is we're using the accelerometer in this part of the model, if you see my cursor, to model the transition states between when your phone is active to when it's at rest versus from when it's at rest to when it's active. So we have these two directions that you can go in this two-state HMM. And you could have chosen to use accelerometer as your outcome and use screen state here, but this is how we chose to set it up. It works fairly fine. And we have our hour of day random effects, random intercept. So here's a schematic of what this PHMM model looks like, but essentially it's this two-state model, and each hour we're looking at these transitions, and then this is our screen count, and then the transition rate depends on accelerometer data as well as your hour of day. Again, if we're looking at active phone use, the active to rest rate, transition rate, that would be pretty high, say around bedtime, right? Because you're using your phone and then you go to sleep, you stop using your phone. And you would expect that when we fit this model to someone, the rest to active rate model should have a very high rate in the morning when you wake up, because you haven't been using your phone and then you wake up in the morning. So sure enough, that's what we see. Here's an example patient. We fit this to one example patient. Here at the top, it's the probability that you're in either one of those two latent states. You can see the time scale here at the bottom. This person goes to bed around midnight, wakes up at around 8 in the morning. And I'll just call your attention to, you can kind of see what the data actually looks like for this person. Here's the screen counts and the accelerometer magnitudes, and they do follow some kind of circadian trend over time. This is multiple days, you can see here on the time axis at the bottom. But what I want to call attention to here is the values of these random intercepts. Remember, we have these two models. We have a separate model for rest to active, and then we have an active to rest model. So for each one of those, we have 24 random intercepts, one for each hour of the day. And we've plotted them here at the bottom. So if you look at rest to active transition, so that's this plot right here, you'll notice that when it's highest is what? At 8 in the morning, 8 in the morning, right? So we're saying this person's waking up around 8 in the morning, and then the transition from rest to active is really high right then. Similarly, if we're looking at active to rest, this is probably going to be highest when they're going to bed. And when they're going to bed, you know, sometime after midnight. So that it's really peaking from like 1 to 4. So they're going to bed pretty late. But essentially, you can kind of see that these random intercepts are corresponding to these sleep and waking habits that this person has. Now, there's one key thing I want to point out here. Remember that these are N of 1 models. We're fitting this for each person. There's a lot of information in the scale of the y-axis for these random intercepts. Suppose you don't have any routine at all. Like when you go to bed the hour at which you go to sleep and wake up is drawn from a uniform distribution from 0 to 24 or something, right? Nobody actually lives that way, obviously, but you could imagine if there was literally no routine, then the random intercepts would contain no information, and the scale of the y-axis would diminish. They'd essentially all be really close to 0. This gives an idea. If we wanted to calculate some kind of trait level statistic for someone that quantifies their overall routine, we propose this diurnal rhythm metric, which is quite simply the variance of these random intercepts actually added together in each model. If they're high variance, that means there's a lot of routine at play, right? The hour of day tells us a lot of information. If there's no variance, there's no routine at all. So we take the variance of these random intercepts, add them together, and that's our DRM value. So let's look at our sample and see if this DRM measure of routine for our individuals correlates to any of our clinically relevant outcomes that we also collected. So first of all, we do see that there's a positive association between their routine, DRM, and mean sleep duration. We looked at a lot of other things. Here you can kind of see these are 3 real patients from the study, one with a low DRM, and you can see their random intercepts contain like very little information, meaning that they're probably going to bed and waking up at very different times. There's no real routine or structure to how they live their life. No offense. And then here's a medium and a high DRM participant. So we also calculated, I think that, we have 2 different, this is, I guess, the Beck Depression Index, and then there were some self-report mood responses that were administered via BWE over the course of the study we just calculated the mean of them. And these were only marginally associated, but the direction of effect was what we would expect. Older people had better routine, and then in this sample anyway, men had a stronger routine than the women. The results relating this back to routine, back to clinical outcomes, they were all in the right direction. Nothing too strong, but it's kind of a nice aside. Remember, we are just using this as a stepstone to estimate sleep. So, how am I doing? Okay. So, we have this measure of quantifying routine. We also have, as an aside, I didn't use that for this DRM, but we have these latent states too. We now have these active rest latent states. We have estimates of them. We're taking essentially the estimates of that latent state, whether or not you're in active or inactive phone use, which remember we've already accounted for missing data. We're basically taking that as an output of this model. And now we want to use that as input into our sleep model. So that's what comes next. So we're going to use the output of our PH-HMM model to get our latent phone use active rest state estimates, and then we will use this to estimate nightly sleep and wake times, accounting for this overestimation bias I mentioned at the beginning. So let's just take a look at some raw data. This is from one participant where, if you're just looking at screen-on data for this person, this is actually someone who uses their phone a lot. And so this is actually a high-quality data person, which is why I'm trying to show them, because even people who have really high-quality data, you're going to get some strange nights like this one, right? Like what's happening here? Each row is a night. Now, if you strictly went by the data, and if you assumed that your use of your phone was a perfect reflection of your sleeping habits, right? Then we would say that this person slept for like 13 hours this night, where perhaps I would say that's probably unlikely, and more likely they just didn't use their phone this evening. Also, similarly, we'd say that they slept the entire day today, essentially, right? Like these are assumptions where if you have a model which is making that really naive assumption that your phone use is reflective of the person perfectly, you're going to come up with some pretty wonky estimates of sleep. So if we were to take that naive approach, another way of thinking about it is if you just, say, maximize the likelihood over your data, where SI is the unobserved latent time to sleep on night I, WI is the unobserved latent time to wake after that night, and if you have T days of data for a person, this is also an N of 1 model. And then X, this is just the input from that PHHMM model from before. So these are our latent states for each hour of the day. So if we just had some likelihood and we maximized that, that would kind of correspond to this naive approach. We're just letting the data tell us when you're awake or when you're asleep with no extra information. And so it should recover what the data is showing us, right? X is kind of telling us when you're active and inactive on your phone. So can we do better? Is sparse data a hopeless case? I've already told you it's not, but hopefully I can convince you in the next few slides. So our approach to this is actually a relatively simple one, but we do a semi-supervised approach. Well, what do I mean by that? So it's not feasible to ask every night over the course of follow-up, especially if it's a long duration of follow-up, about when they went to sleep or when they woke up the next day. But what if we just ask them once? What if we just ask them, say, in baseline, as you know, if you have like the PSQI or something, oftentimes a lot of studies already have this question built into them, or you say, where do you go to sleep on average? When do you go to sleep on average? When do you wake up on average? So let's say that we have that. Let's call that μS. This is your self-reported average time to sleep. And μW is your self-reported average time to wake. It's, I'm leaving it simple for now in terms of the notation, but you can easily also have one for weekends and weekdays, and if you want to get even finer than that. But the point is, if you have this self-reported average time to wake and sleep, how can we incorporate that and fix our naive approach and adjust for this overestimation? So with μS and μW in hand, quite simply, what if we just maximize some kind of penalized log likelihood, right? So we have our naive approach from before. This is what the data alone would tell us. But now we're kind of penalizing the empirical mean of our sleep estimates from μS. So, and then we're penalizing the empirical mean of our waking estimates from when you told us your average time to wake was, right? So we're kind of forcing our model to align with what you said your average time to wake and your average time to sleep was. It's a pretty simple idea, right? But what I like about this idea is that the amount of data that it includes, I guarantee you that many of you who are collecting data probably are asking, maybe in baseline, that precise information, right? So if you incorporate that information, you can go 90% of the way of fixing the bias that would cause if you just trusted your data as is. So let's see how this approach does. I will add as an aside, we also developed a completely unsupervised approach where essentially we use population-level distribution data on sleep duration to come up with, combined with your data, to come up with estimates of μS and μW if you don't have them providing that to you directly. And it doesn't do as well as the semi-supervised approach because we're leveraging population-level data, but it still is better than going with the naive approach, as we'll see. And we have some nice properties. I think we show that asymptotically we have a reduction in the bias. It doesn't get rid of it all the way, but this unsupervised approach, this is if you come in just with the passive data and you have literally no self-report, and can you still do something? And the answer is yes, and something that would still be usable. So let's look at a couple example participants. So this is the naive approach. This is for someone who actually had pretty good data. And these X marks, in this particular study, they were asked once a week when they went to bed and when they woke up on average over the previous week. So you can think of this X as saying like they were, each row beneath this, the previous 7 days, they thought back over the previous week and said, oh, I woke up at around 7, I went to bed at around 11, right? And that's what these kind of correspond to. So you can imagine like drawing a line down. And so in this case, actually, they said the same thing in 2 consecutive weeks. But nonetheless, this is you can kind of think of this as we want our method to recover the red X's, and the red X's kind of correspond to the entire previous week before that. Now, in this case, the unsupervised approach, it's a little all over the place. It could be a lot worse than this, to be honest. But you still get, for example, a couple completely unreasonable sleep estimates. I guarantee you that if I put these sleep estimates in front of one of my clinical collaborators, they'd laugh me out of the room. They wouldn't want to use this in any of their analyses. They'd say, they didn't sleep for 14 hours that day. I know they didn't. And you want to be able to put a digital biomarker in front of someone that they can trust, that we can validate, right? So, and this is one of the good patients. I'll show you another one in a couple slides that's a lot worse. So what happens if we do the semi-supervised penalization? Well, it actually tamps it down a little bit. It does actually draw it closer to the self-report. I will also say that we used the PSQI for this. We didn't use these red X's, right? That would be a little bit cheating, right? If we forced if we're evaluating it, the performance of the method based on the red X's, and we're explicitly penalizing our method to match the red X's. So we're using baseline only. We're not using these mid-study assessments to judge this. And so if I just flip between these, you can see unpenalized, and then when we penalize it, right, the 14-hour night rest goes away. Things look a bit more reasonable. And actually, you know, if you look at these, their self-report, actually, the average of these is probably around here. The average of these is probably around here, right? It's actually matching up to what they would have said. This is another participant. This is someone who has really sparse data. They don't use their phone very much. And if we don't penalize, look how terrible this is. You would never report this. You would never use this data if you just went with the naive approach and trusted the data without accounting for sparseness. So when we penalize, it really brings it down again, right? So if you look at these two, when we incorporate a little bit of their own information, a little bit, we do the semi-supervised approach, suddenly we get something which is usable and is definitely reflecting reality much better. So what would happen here? It's a good example to think, right? The naive approach would say they slept this entire duration here, whereas once we penalize, we might actually say, hey, you know what? Probably not. Like, maybe they're just not using their phone here. So this is not perfect, but that's why we have to validate these measures against, we need external ways of validating these measures, and which we've done in this paper. So as a final example, actually, I'll show this. This is similar to the previous plots, but these gray dots kind of correspond to the latent state probabilities from our PHHMM model. So rather than just telling you what the value of X is in terms of is it inactive or active phone use, we're actually seeing these probabilities themselves. And you can see the dotted or the dashed black line here. This is the naive approach. It's completely mirroring when the phone is said to be active. It's basically trying its best to just fit to the gray dots, right? So it's saying like, okay, you know, you're pretty much sleeping here, you're pretty much sleeping here, pretty much sleeping here, and you're pretty much sleeping this entire duration, right? Whereas once you add in the penalty, we're getting something much more reasonable. So this is a similar figure to the ones I showed before. All right, well, I'm only showing you examples. Let's apply it to the entire data set. So we looked at the average mean absolute deviation of sleep estimation compared to self-report over the course of the study, those red X's I was telling you about. And what we found, so this is in hours. Basically what I'm saying here is that for sleep duration on any given night, our estimate of sleep duration, if we just trusted the data without using any self-report, and we just thought that the smartphone was a good proxy for human behavior, we would overestimate sleep by about 2.5 hours every night. That's under this, and we have other competing approaches which can be even worse. But like for every approach, right, you can't do any better. You're always overestimating by 2.5 or more hours in sleep duration. And the unsupervised approach, right, where we're leveraging population level data in the absence of any self-report, it does reduce the bias a bit, but we're doing the best when we're actually incorporating the PSQI and just using the mean time to bed, mean time to wake as our mu-s and mu-w in our semi-supervised framework. And we actually get down to getting within about a half hour, right, of sleep duration, which is pretty good. And it gets quite usable, despite how sparse the data can be. So this is averaged over the entire data set. So I think I'll leave it here, but from a broad level, I'll just say, oh, that's exactly 25 minutes. We've talked today about a lot of different data processing platforms, and I just wanted to, my talk was a bit more focused on a particular sleep, digital biomarker, like focusing on sleep. But, as important as it is to come up with standards for data outputs and inputs to a lot of these data processing platforms and data formats and things like this, we also need to continue to come up with quality, validated digital biomarkers themselves in a lot of these domains. It's easy to do maybe well, maybe not easy to do, but we've made a lot of headway in some, but I think we're very underdeveloped in a lot of domains, including sleep. And so, we can't forget about that along the way. So thank you very much.
Questions?
Yeah.
This is great. I was wondering for the penalty, whether this may not be possible because your goal is to look at duration, but if you could actually penalize based on duration awake and duration asleep. So if somebody's sleeping more than like their average from the past X days,
Yeah.
have you thought about that rather than looking at
Actually, yes. The first version of this, we actually had a lambda S, lambda W, and lambda D, lambda duration, which in essence what it does is it imposes correlation on SI and WI. It wasn't actually helping too much relative, like we ended up taking it out because incorporating it was not improving estimation over lambda S and lambda W. But no, it's funny you say that. That was actually our first approach, was to include both a penalty on time to bed, time to wake, and its duration. But
if you've done duration of sleep and duration of wake instead of time wake, the time to wake.
oh, duration of awake. Yeah. So actually, one of the competing methods, this SML is actually focused exclusively on, it's like sleep maximum likelihood. It basically is only focusing on the sleep portion, and it's not caring about the awake hours. SW is sleep-wake maximum likelihood. So this is actually kind of taking your full 24 hours and calculating your likelihood over the full day rather than just the night. It's not exactly getting at what you're talking about because we're not explicitly modeling duration of when you're awake, but these two methods are a little bit comparable in that, like, the SWML, which is the approach we use, does in our likelihood gives waking hours the same weight as nighttime hours, whereas SML does not, right? It only focuses on the sleep.
Other questions?
All right, thank you.
I think
Oh, yeah.
I have a question about the HMM model.
Yeah.
Was it multi-level with respect to the patients as well, or is it only with respect to the time?
No, these were each done within one patient. Yeah. And so, being only a two-state model, and we didn't have that many parameters to work with, and so with 3 months of data, it was pretty feasible to do. That being said, ideally, you'd want to be able to apply this to someone who had less data, and certainly I could see extensions to this model that would allow for incorporation of sample-level information. There's no reason to have to do, especially because the relationship between accelerometer and screen state, that's got to be fairly universal, right? Like, it doesn't matter who you are, if you're having a lot of screen-on events, your accelerometer is also going to be fairly high. So, like, there should be population-level associations between these two, which you could leverage. But I haven't, not here, no. Didn't need it in this sample anyway.
Yeah, I actually have a very small question.
Yeah.
And I think that when you incorporate like a multi-level, you need to sort of cluster also into say like, well, these have like similar routines.
Yeah. So I will add that the first time, so this was work done by Benny Wren. He's a third-year PhD student in our program at Penn. And the very first time that he implemented this we actually did it at the population level, but the number of random effects that were involved, because we wanted to have a different hour of day random effect per individual, right? This is, that definitely has to be specific to the individual, right? Everyone has very different time to bed and time to wake, et cetera. But the number of, basically we were having a lot of trouble fitting that model. It was just so many random intercepts that were being estimated that we ended up going with the N of 1 approach because the data allowed it. All right, thank you.